Okay, chapter 8 is called Sequences and Series, and here's 8.1, defining and using sequences and series. So first off, a sequence. A sequence is an ordered list of numbers. Okay, and then rather than defining a finite sequence and an infinite one, I'm just going to show you an example. Here is a finite sequence. It's an ordered list of numbers, right? So this one's finite because it has an end, as opposed to this one, because I've got the dot, 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 that just means it goes on infinitely, okay? It's infinitely long. This one is finite as a finish, okay? All right, so often we'll use this sort of notation where we've got, this would be sequence A, okay, and we've got that little n. So we call this A sub n, all right? Yeah, sequence A. I said this out loud, sequence A. Okay, and we've got, they just give us the value of the different terms here, okay? So the 2 is going to be term 1. Okay, so I could say A sub 1, that means the first term of sequence A. I don't know, I made my A in a different way, but so the first, that's going to be 2, right? So, you know, A sub 3 would be 6, for example. A sub 5 would be 10, okay? Yeah, A sub 4, here I'll make my A like that this time. The value of that term is going to be 8. The term number is 4 because it's the fourth term. The value of the term is 8, okay? All right, so next up, we're going to find the first 5 terms of this sequence, of sequence A here, okay? So this is called an explicit formula. And that just means that you plug in the term number to find the term values. So I'm writing plug in term numbers to find term values. Okay. So all I have to do is replace, you know, instead of A sub n, I have A sub 1. So that just means I'm going to replace the n in the formula with the number 1. So I have 3 times 1 minus 2. Okay. On the next one, it's going to be 3 times 2 minus 1. It's always going to be 3 times something minus 1. The something is whatever the term number is. So you can use the term number to generate the value of the different terms. So the only thing that's changing here is what's in the parentheses, and I'm just putting in whatever term number I'm on. Okay, and then I would want to simplify these. I got 3 minus 1 would be 2. 6 minus 1 would be 5. 9 minus 1 is 8. 12 minus 1 is 11, and 15 minus 1 is 14, okay? And you could write those in a list from left to right if you wanted, I don't care. But there's the first 5 terms, okay? All right, so that's what a sequence is. It's just a list of numbers, as opposed to a series is the sum of a sequence, okay? So if you've got a sequence, this is the same sequence we had before. We had a finite one. And if you add up all of the term values, that's going to be a series instead, okay? So if I'm asked to evaluate this series, I just actually do, so this is my series. And if I'm asked to evaluate this, then I'd actually add it up, and that would give me 20 here. So this is the sum of that series, okay? So this is what you do if you're asked to evaluate a series. Okay. Now, really, at this point, we can only evaluate series if they're finite, if they end. This is going to be infinitely large. There are certain series that we can evaluate that are infinite, but we'll get to that later in the chapter. Okay. So this is my series, but I can't evaluate this because it's going to be infinitely large. I'm adding bigger and bigger things, right? So we could sit there all day with a calculator, but the numbers will just be getting bigger and bigger as we add more terms in. So you could say that the sum of this is infinity because it's infinitely large, or you could say no sum because it doesn't really have a sum. You can't really add it up. It's just always increasing in value. Okay. All right. Got another example on the next page. So, oh, and I gave it's the same series from my previous example, actually. I've got the same formula here. Okay, so we've got this S though now because S is for series. So now this is going to be a series, and you know the series, it always has a related sequence. Okay, so you know like this is related to 2, 4, 6, 8. This is a series, but it has a related sequence. Okay, so often you'll see S instead of A when we're dealing with a series. Okay, so if I want to find A sub 5, that means I want to find the 5th term in my sequence. So that is where I'm just going to plug in 5 for n. So 15 minus 1 would be 14. Okay, so there's A sub 5. There's the 5th term in my sequence or series. Now this says find S sub 5. So this means find the sum of the first 5 terms. That's what this is telling me to do. Okay, so since I've already expanded this, this is the same from that previous problem on the last page. Okay, so I know this is going to equal, it's going to be 2 plus 5 plus 8 plus 11 plus 14. So I'm not going to go through finding the value of all those terms because I've already done that. But you could, right, if you were doing this from, 2 plus 5 plus 8 plus 11 plus 14. You could, though, create those from scratch just by plugging in the n values, okay? So find S sub 5. Well, S sub 5 is going to be the actual sum, okay? So remember this. So sometimes you're asked to expand a series, and this would be my expansion, just showing the value of all the terms. And then finding the actual sum is right here. Okay, so when it says find S sub 5, that's the sum of those terms. Okay. All right. Next up, we're going to get to sigma notation. It looks like this. It's kind of intimidating if you haven't seen it before, but it's actually really easy to use once you learn what the symbols mean. Okay. Sigma notation is sometimes called summation notation. So those are interchangeable. Okay. I'm going to usually use sigma notation, but you might see summation notation sometimes. Okay. And we're only going to use sigma notation when we've got the sum of a series. So we're only going to use this for series. Okay. All right. So this is this E, capital E looking thing is the Greek letter sigma. It's the uppercase sigma. Okay. So there's always going to be a number on the bottom of the E. It might say n equals 1 or g equals 1 or whatever, but there's some variable, and it's usually going to equal 1. It can equal other things, but this symbolizes a start to our sequence. Okay, and I'll explain what I mean by that in a second. But the number on the top is going to symbolize the end. Okay, so I call this part, what's to the right of the E, this is my term builder formula. That's not a technical term, but that's just what I call it, because that's what this part does. So this is a little expression that will help me build the different terms, okay? So what I'm going to do when I'm asked to expand this, I'm just going to plug in all of the integers starting with 1 and ending with 3. So the integers from 1 to 3 are just 1, 2, and 3. And the place I'm going to plug those in is right here because my k values will go from 1 to 3, just the integers from 1 to 3. So I'm not going to put in 1.7 or anything like that. Just 1, 2, and 3. I'm going to plug in to this formula for k. Okay, so my first term, I'm going to get, I'll put my first term in brackets here. I'm going to do 2 times 1 plus 1. Okay, my next term, since this is a series, I'm adding together my terms, right? Then I've got 2 times 2 plus 1. And finally, 2 times 3 plus 1. Okay? So when I'm asked for the expansion, I'd want to simplify each term. Okay? So my first term, yeah, it's going to be 2 times 1 plus 1. But that would be, let's see, 2 times 1 plus 1. That would give me 3. So my first term simplified is 3, right? Then I've got 4 plus 1 over here, which is 5. Okay? And 6 plus 1 is 7. Okay? So this is an expansion of 3 plus 5 plus 7 means the same thing as this, okay? And it might seem like, well, what's the point of that then? Why would I want to write it like this if I can just write 3 plus 5 plus 7? Well, imagine this we're plugging in everything from 1 to 77. Well, then there'd be 77 terms, and it would take me a long time to write out the whole thing, but I could write it in this sigma notation very quickly, okay? So this is my expansion here. And then evaluating it, I just do the math. So 8 plus 7, 15. There's my actual sum. Okay, I've evaluated that that sequence. Okay, a series, I should say. Okay, now notice this one we're starting with 2. We don't always start with 1, right? So when I'm building this first term here, I'm doing 3 times something minus 1, and this time the something I'm starting with is 2. Okay, so I'm going to plug in everything from 2 to 6, all of the integers from 2 to 6. And I'm plugging into 3 times something minus 1, right? Gotta start writing smaller. I'm bad at spacing these out. Okay, so then, for my expansion, I'm going to just clean up each term. So let's see, I've got 6 minus 1 would be 5. I got 9 minus 1 is 8. Got 12 minus 1 is 11. 15 minus 1 is 14. And 18 minus 1 is 17. There's my expansion. And then you just add them all up to evaluate. And it's all going to come out to 55 there. Okay. All right. So let's expand some more of these and evaluate them. This next one is a little weird because there's no valuable here. Yeah, I'm plugging in 1, 2, and 3, but into what? Into nothing. Okay? So what this means is, I'd be plugging in 1, 2, and 3. There's nowhere to plug in the 1. This is called a constant series because my first term, there's just a 7 there. There's nowhere to plug in the k values. So that's just going to be the value of my first term. So this is going to be a sub 1, okay? And my second term is also going to be 7. All the terms are going to be 7. So really, I just have to figure out how many terms I have, and it's going to be everything from, I'd be plugging in 3 different things, even though there's nowhere to put them in. So there they are, right? So my expansion is just going to be 7 plus 7 plus 7. Okay. And that means when I evaluate, I'm going to get 21. Okay. So that's called a constant series when your term builder part is just a number. Okay. So if C is just a number, that I got C for constant. Okay. Okay, and when we're starting with 1 on the bottom, which we usually will be, then if you think about the number of terms you're going to end up with, it's going to be represented by the number on the top because I'm going to go from 1 to something. Like on the last one, I went from 1 to 3. So that means there were 3 terms, right? So if n is 17, there's going to be 17 terms, okay? So this can represent the number of terms. Okay, So a quick way to do this is just take whatever the constant is and multiply it by the number of terms, okay? So in the last one, I could have done 7 times 3, right? 7 times, and there's 3 terms. So it's just a nice quick way to do that. Now, yeah, there's going to be 28 different terms here. They're all going to equal 6. I could expand the whole thing, but if I just saw this and was asked to evaluate, I just think, okay, every term's going to be 6, and there's going to be 28 terms like that, and then you can just do the multiplication, which would come out to 168 here. Okay? Okay, had to make a little cut there because I made a mistake. Hopefully that doesn't look too weird. All right, so next up we've got this problem that says find the sum of the first 100 natural numbers. Natural numbers are just counting numbers. So I'm finding what 1 plus 2 plus 3 plus 4 all the way to 100 would equal. Okay, so there's a very famous story about this. So this is what most of us would do, okay? And there is a very famous mathematician named Carl Friedrich Gauss. And as the story goes, his teacher in school gave this problem to the class to kind of keep them busy a little bit and give them some arithmetic practice. But he figured out a much quicker way to do this than adding the numbers up from the smallest one to largest. Most of us would say, okay, we got 3 plus 6, and that's going to be 10, and then keep adding the next number and the next number. What he did instead is he paired the numbers. So he took the smallest number and the largest one, added them together, okay? And then if you take the second smallest and the second largest, add them, you're going to get 101 again. And then the third smallest and the third largest gives you 101. So it keeps getting those sums of 101. And if you keep doing this until you get to, you're kind of working to the middle of the sequence, the last pair that you'd get to would be 50 plus 51, okay? So then you just thought, well, how many pairs am I going to have? So this is my first pair, second pair, third pair. I'm going to get all the way to 50 pairs. Each one of those pairs has a sum of 101, and I can do that multiplication a lot quicker than doing all of the addition. So that multiplication is going to come out to 5,050. Okay, so he got the answer really quickly, amazed his teacher, became famous, and lived happily ever after. And that's the end of the story. Okay, but from this method, we get a formula for the sum of a linear series. Okay, so a linear series is when we just have a variable as our term builder part. Okay, so like in these two examples here, I just have k. So you could expand this out. This would be that series we were just talking about, right? It would be 1 plus 2 plus 3 all the way to 100. Okay, so here's how the formula goes. If you take the number of terms times the number of terms plus 1 and divide it by 2, it's going to give you the sum of the entire series, no matter how large it is, which can save you a lot of time. Okay, so if we think about this, this is this last example, really, right? So take the number of terms, which isn't 50, that's the number of pairs. So the number of terms, it's the first 100 natural numbers. Okay, and then if I take 100 plus 1, that gives me 101. And I'm going to divide this by 2. And looking at this, compared to what we got up there, well, 100 divided by 2 is just 50, right? So this would be the same as 50 times 101. And that's going to come out to 50/50. But the nice thing about this formula, if you memorize it, then you can just think, oh, okay, I'm going to have 29 terms here. I'm going from 1 to 29, so it would be 1 plus 2 plus 3 all the way to 29. But I'm going to take the number of terms times the number of terms plus 1, divide that by 2, and I can get my solution really quickly. It's going to come out to 435 here. Okay? So that's a linear series. Okay? And then the last type of series we're going to look at for today is a quadratic series. Okay? So this would be, 1 squared plus 2 squared plus 3 squared, depending on how far I'm going. Okay? And I don't have a story about where this formula comes from, so I'm just going to tell you what it is. It starts out the same, right, as the last one, but then we've got another binomial in here, and it's all divided by 6. And if I'm being totally honest, I don't know where this formula comes from, but I do know it works. So it's worth knowing about, okay? So on this example, I've got 1 squared plus 2 squared plus 3 squared all the way to 17 squared. But let's try this out, which you're welcome to expand that by hand. But let's try out this shortcut, okay? So n, that's the number of terms, is going to be 17. And then I'm going to have 17 plus 1 in here, and 2 times 17 plus 1. This is all going to be over 6, okay? So let's start simplifying this. Okay, 2 times 17 is 34, plus another 1 is 35. Okay, and if you multiply on top and then divide by 6, it's going to put you at 1785, a lot quicker than finding the value of all of the terms, expanding the whole thing, and then adding everything up. Okay, and likewise here, this is the same kind of deal. We're just going to have 22 terms, and then 22 plus 1 would be 23. And then, just to make sure I don't mess up, I've got 2 times n plus 1. This is all over 6. So let's see, this is 44 plus 1 would be 45. Okay, and let's see. That's something that I can simplify quickly on my calculator, but it would take me a long time to expand and evaluate that by hand. Okay, and that's it for today. See you next time.